Thanks a lot for the introduction. So hi everyone, thanks for being here. My name is Eryk and I'm a data scientist at Dexter Energy. And today I want to talk to you about time series forecasting in the energy domain, and more specifically about probabilistic forecasting. But before we get into that, I think it makes sense to understand the energy markets a bit better and also understand why we actually need the forecast in the first place. So the story starts with climate change, and climate change is one of the biggest challenges of our times. It has led to an increase in extreme weather events, natural disasters, and rising sea levels. So as such, it poses an existential threat to humans across the globe. And one of the biggest drivers of climate change is the vast emission of greenhouse gases to the atmosphere over the past century. So out of this emission, around 73% comes from energy sector. So a big chunk of this 73% actually comes from thermal plants powered with fossil fuels. And fortunately for us, we can actually replace quite a bit of that with renewable energy. Therefore, to mitigate climate change, we need to transition. And the transition to renewable energy sources is not only a very important strategy in the battle against climate change, but it also enables sustainable growth of our ever-increasing electricity needs. So that is why we can see over the past years an accelerating increase in the introduction of renewables into the grid. But this comes with a big challenge, and the challenge is all about balance. So the energy grid always needs to be in balance, so the supply must meet demand. In other words, this means that at any moment, the amount of energy going into the grid must equal the amount being taken off the grid. So otherwise, the frequency will either rise or drop, and for us, this means that our devices might actually break if the frequency is off by even 0.25%. So why is this such a big challenge? So with renewables, the energy supply is intermittent and to a large degree unsteerable. So here you can see the actual wind and solar power generation over a span of 4 days. So it looks like this because, well, non-steerable means that it happens when it happens. So when the wind blows or when the sun shines. So we need to transition from a demand-driven system to a supply-driven system. So with the demand-driven system, we could simply spin up more thermal plants, possibly powered with fossil fuels, whenever the demand was high. With the supply-driven system, we need to adapt to the new generation model. So the demand is most often not flexible. So in order to allow for some kind of scheduling of consumption to match production, the renewable energy suppliers need to predict and report their expected generation in advance. And this happens on the energy markets where participants can buy and sell energy. So there are quite a few different energy markets, but today we'll focus on the day-ahead market. So you can see the T-1 on the timeline. And basically what happens is that on the day before, at noon, the energy suppliers need to declare how much energy they will generate. So then at time of the delivery, T0, whatever was promised needs to actually be delivered. And soon we'll see what happens when that's not the case. So for the time being, let's see that our hypothetical renewable energy supplier decided to sell 200 megawatt hours on the day-ahead market for the price of 90 euros. So what would have happened if they decided to sell a bit less? So there will be less supply, which would actually increase the prices because energy becomes more scarce. So you can see that this is the basic mechanism of how the market matches supply and demand by dynamically adjusting the price so that the balance is ensured. So now let's look at a case where the wrong amount of energy was sold on the day-ahead market. So our hypothetical energy supplier decided to sell 100 megawatt hours, but they only generated 80, which resulted in a shortage of 20. So at the time of delivery, this means that actually this energy needs to be bought back at the balancing market, and then it comes at the price of 300 euros. So you can wonder why this price is so high, and that's probably because everyone on the market might have the same problem. So everyone might have over-forecasted their generation, which leads to a general shortage. And when there is a shortage on the grid, this means that the price on the balancing market goes up, and we are in the negative imbalance. So you can think of this imbalance as a kind of a penalty for destabilizing the grid. So the imbalance cost can be calculated as the difference between power multiplied by the difference in price. So in case of our energy supplier, this means that, well, they were 20 megawatt hours short, and there's a 200 euro price difference between the day-ahead and balancing markets, resulting in a hefty penalty of 4,000 euros. So another way of thinking of this penalty is that it is basically a payment to another supplier, possibly a thermal plant, again powered with fossil fuels, to step in and balance the grid. So this, as you can see, leads to a very unfortunate scenario in which money from a sustainable energy source flows into the unsustainable one. So that is why the unpredictability is such a big problem for renewable energy suppliers, because their energy supply is intermittent and very hard to predict. So now let's recall the formula for the imbalance cost, which is with its two unknown quantities, so the volume and the price. So if the energy supplier actually has the power forecast and price forecast, they can arrive at an optimal trading decision. So in the price forecast, we already also have a bit of information about the uncertainty present in the market. So let's now look how the price forecast can help with stabilizing the grid. So we have the very same scenario here. Just now our supplier also knows the predictions. So for the sake of this example, let's assume that the predictions are correct. So they know that they will generate 80 megawatt hours, and they also know the prices. So now it would be interesting to think what they should actually do on the day-ahead market. So there are 4 options here, and let's do a show of hands. What do you think they should do? So of course, remember the potential imbalance costs that they could incur. So who thinks that we should sell as much as we can? If you can, raise your hands. Okay, no one? Let's see about option B. Who would say that we should sell nothing? Okay, again, no one. Oh, one person, okay. Nice, thank you. What about option C, sell a bit more? Okay, a few hands, nice. And the option D, last one, a bit less? Okay, most of you. Cool, so yes, option D is actually correct, so sell a bit less. But option B, so thanks a lot for raising your hand, is also quite interesting, so I'll come back to it in a second. So let's look what happens if we sell a bit less. So we forecasted 80, we decided to sell 75, so we have a surplus of 5. And we can use those 5 megawatt hours to potentially help balancing the grid. And then the market dynamics will also potentially lower the price difference because there is less grid imbalance. So as a result, we will get a reward for helping to stabilize the grid. And the reward is again calculated using the imbalance cost formula. So in this case, we would get 500 euros reward. So why shouldn't we actually do what option B suggested? So hold back everything we generate and actually sell it on the balancing market. So there are 2 reasons for this. The first one is the so-called price maker effect. So if we substantially reduce the quantity on the market, this will also drastically impact the prices and will potentially flip the market into positive imbalance. So then we are left with 80 megawatt hours. The market is in the surplus state, and we might incur a penalty, potentially a very big one, for flipping the market. So as you can see, this is another of the market dynamics that basically incentivize everyone to act in its best interest. So there's also the second reason, which is connected to our risk appetite. So how much financial risk we actually want to take in this particular situation. And if we take everything into consideration, this actually suggests to avoid either all-in strategies or zero output ones, and just decide to trade a bit less. So now let's look at the forecasts. So we start with a point forecast, and here you can see the time series of actual energy prices. And at time t-1, we actually want to create predictions of the next few observations in the time series. So basically the trajectory of the future prices. But yeah, as the title suggested, we want to harness the uncertainty and embrace it. So we are also predicting the percentiles or quantiles, which represent various uncertainty intervals. So in this case, what we get is basically a probability distribution for each point in time in the future. So if we take a slice through the data, we will obtain this probability density function. So what we see here is the price on the x-axis, the probability mass on the y-axis, and basically this plot tells us what are the probabilities of the possible future outcomes. So if we look at this PDF, we see Q80, which basically indicates that 80% of observations should fall below this particular value. So knowing this and our risk appetite, we can already make a trading decision. So in this particular case, we might assume that the price will be positive because most of the probability mass falls on the right side of the y-axis. But that might be quite different if we actually predict this PDF with an interesting bimodal distribution. So here, our trading decision might be different because we can expect a small but, well, relevant probability that we will actually end up with a negative price instead. So this, of course, impacts our potential trading decision, but we also need to account for our power forecast and our risk appetite. So what do we think about the trade-off between potential gains and losses? So now the question is, how do we actually get the probabilistic forecasts here? So here you can see a basic forecasting pipeline, and we treat it as a time series regression problem. So we have a model, and this can be any model like statistical model, machine learning, deep learning. Then we have quite a lot of features. So this can be market prices, grid data, autoregressive features. Then we also use quite a lot of weather information, so temperature, cloud coverage, wind speeds, humidity, sunshine, and many, many more. And what we should also include is the price maker effect that I discussed before. So we should actually account for our own behavior. So we should have some kind of a causal model where we try to predict the prices, but at the same time, we include our own actions in the market. This is actually very close to the secret sauce of Dexter, so I will leave this outside of the scope of this talk. And for the time being, we will focus on a simpler assumption, which is a price taker assumption. So we assume that we don't actually impact the prices on the market. So now, seeing this, the question is, how do we get a PDF that we can feed into the optimization engine? So as always, we can start with a simple baseline approach. So what we can do is we can take a point forecast model that we maybe already have. We can create predictions on a calibration set and get the error distributions. And then whenever we want to create a new prediction for, unknown future, what we do is we use the point forecasting model. We then use the point prediction as the mean of the new distribution and overlay it with the error distribution from the calibration set. So this simple approach has quite a few nice characteristics. So basically, it is distribution free. So it assumes any distribution that is present in the data. And also, it guarantees that the quantiles are correct. But it also, of course, comes with a downside, as it's a very simple approach. So we use the same error distribution for pretty much any new predictions we make. So there is no variation at all. So at this point, I think it makes sense to also discuss what actually defines a good probabilistic forecast. So there are two concepts here. The first one is calibration, and calibration is all about the alignment of the predictions with the actual situation. So if we think about the 20th quantile, we would expect 20% of the observations from the test set to fall below that value. So what we can do to test this is we can use a QQ plot, where on the x-axis, we plot the theoretical quantile we are trying to predict. On the y-axis, we plot the sample quantile from the test set. And basically, the data from the test set can be either a calibration set or a test set. And then if the model is properly calibrated, the points will fall along the diagonal line. So basically, Q20 will match exactly Q20. But now let's look at the case, what happens when we have a poorly calibrated model. So here you can see that Q20 maybe aligns more with Q40 instead. So this leads to a coverage error. So of course, that's not something we would like to have, because we aim for a straight line alignment indicating perfect calibration. But at this point, it also makes sense to realize that even a perfectly calibrated model doesn't guarantee good predictive power. So it can be the case that we have predictions with a very wide uncertainty interval, and that pretty much limits the usefulness of those predictions for the business. So this can be a case with, for example, the baseline approach, where we use the same intervals for every new point, and the intervals tend to be quite wide. So this brings me to the second metric here, so sharpness. And sharpness is about the concentration of the PDF, so how narrow it is. So here you can see one PDF, and the other one is quite different. And the second one is definitely more useful for decision making, as it is narrower. So now I will show you a metric that actually combines both of these two. So the metric is called continuous ranked probability score. And to calculate it, we start with a PDF, and then we transform it into a cumulative distribution function by summing up the probabilities so that they sum up to 1. And what we do then is we calculate the area between the CDF and the actual value. And the actual value here is represented as the horizontal line on the x-axis. And here you can also see the Heaviside step function in the formula. And that is used to determine actually on which side of the actual value the prediction falls, and which areas needs to be summed. So CRPS, as I mentioned, combines the two metrics before, so calibration and sharpness, but it also has a nice property about interpretability. So that is because CRPS can be considered a generalization of the mean absolute error. So if we have a point forecast, denoted here with the dotted line on both the PDF and the CDF, we can see that on the CDF plot, it is actually a step function. And if we apply the CRPS approach to it, we can see that this is equivalent to the MAE. So this results with, of course, some simplifications in mind, in the outcome that if we have a CRPS of, let's say, 10 euro, it means that our probabilistic forecast is on average 10 euros off. So this makes it quite practical and interpretable metric. So now coming back to the probabilistic forecasts, we already discussed the baseline approach, which had quite a big downside of having the same width of uncertainty intervals for all data points, which makes it not that useful in practice. So we would like to have our uncertainty estimates conditional. So that is important because uncertainty is not always consistent. So you can imagine that the uncertainty on a sunny day, or the uncertainty profile on a sunny day, is quite different from that one on a cloudy day. So this, in statistical terms, this is called heteroscedasticity, where the variance is basically not constant. So to obtain the conditional uncertainty estimates, we can use 3 of these approaches. So quantile loss, quantile forest, and quantile binning. And all of them are related to quantile regression. So let's start with quantile loss. And quantile loss is basically adapting the loss function to over-penalize under or over predictions. So here you can see the L1 loss, where basically the weights are identical to the absolute ones. So this is symmetrical, and there is no over penalty for either under forecasting or over forecasting. But we can also see the example of Q20, so the 20th quantile, and here you can see that we are over penalizing under forecasting. So the model tends to focus on minimizing these errors. And as such, it will shift its predictions downwards, resulting in lower values. So also, on a side note, quantile loss is also called pinball loss, probably because this plot resembles the movement of a pinball. And fortunately, we can easily adjust quite a lot of regression models to use quantile loss. In this case, you can see that we apply it to LightGBM. So if we put the Q20 on a PDF, and then if we do the same for Q80 and any other quantiles, so in this case, we change the alpha hyperparameter, we will actually get the PDF. So the second approach is in theory similar to quantile loss, but the way we get there is different. So here what we are doing is we are aggregating ensemble predictions. So we start with random forest, then we have the training data, then we create bootstrap samples, and for each bootstrap sample we train a tree. And what we can do is we can fully grow the trees, so we are not restricting their depth. And then the difference here between the quantile forest and the random forest is that instead of just storing the mean value in each leaf, we store all target observations. So then at prediction moment, what we are doing is we are aggregating all the targets from the leaves, and we build a probability density function. So in practice, it might not be a good idea to fully grow the trees because of, well, one, overfitting, and another problem can be sparse leaves, basically when it is difficult to accurately estimate the target distribution because there is not enough data. So what we can do to overcome this is we can either store the training samples in all leaves, or we can use histograms and weight them properly. So yeah, this is quantile regression forest in a nutshell. And the third approach is, again, very similar idea, just the execution is different. So what we are doing here is we are reducing the quantile regression problem to a classification problem. So what we need to do here is to first bin the target into intervals. So you can see here that the target is binned into 0 to 10, 10 to 20, 20 to 30, and potentially more. Then for each observation in the training sample, we use one-hot encoding on the target, as you can see here on the screen. Then we need to train a model, and this can be any multi-class classifier, as long as the probabilities sum up to 1. Or what we can do is use a 1 versus rest classifier from scikit-learn, and then basically we can use any classifier we want. So at prediction time, we take those predicted probabilities, convert them into a histogram, and then if we want, we can also convert it into a PDF. So one potential drawback of this method is that it can result in very noisy PDFs, especially when the feature space has very few samples. But this is a well-known problem of this approach, and it also highlights why it is very important to properly evaluate our probabilistic forecasts. So this brings me to one of the last topics I wanted to discuss today. So there is a common problem of all the approaches I mentioned. And while in theory they should provide well-calibrated probabilistic forecasts, in practice they rarely do. So that is because of either overfitting or noisy data. And yeah, we would like, of course, those theoretical guarantees to hold. So for example, if we have the 40th quantile, we would expect 40% of the observations to fall below that value, and no more and no less. And yeah, if we are using improperly calibrated predictions, this can lead to bad decisions, and we can make a bad trade that will pretty much destabilize the grid. So one of the frameworks that is used for addressing this and gained quite a lot of popularity recently is called conformal prediction. And in a very basic form, we can think of it as an ad hoc post-processing step for our quantile regression. So I will walk you through the steps now. So we start with our quantile regression model. So this can be, for example, a model trained to predict the 40th quantile. Then we take the calibration set, create the predictions, extract the error distribution. And then we compare the predicted quantile to the sample quantile from the error distribution. And if we, for example, see that the number of observations there is lower than the predicted quantile, this already hints at poor calibration. So what we can then do is use a correction factor, which you can see here, to adjust our original quantile prediction, and this ensures coverage. So using conformal prediction, we basically obtain a well-calibrated prediction under, mild assumptions, and a nice extra benefit is that it is distribution-free. But there is also there is a crucial assumption of conformal prediction, which is exchangeability, and this basically refers to the samples being independent and identically distributed. So as you can imagine, in the case of time series, that is not really the case, because non-stationary time series basically well, reject this IID condition. So to overcome this, we can use a rolling window approach where we estimate this correction factor using a rolling calibration window. So yeah, conformal prediction is still a very new field with active research. There are libraries that can help us with implementing this, for example, MAPI. And yeah, I linked to a few resources that maybe now in hindsight they are not super visible, but they are here on in the left corner. And yeah, this brings me to the last topic for today, which is, well, we discussed quite a bit about price forecasting, but we also have power forecasting and how do we combine these two. So power forecasting can also be thought of as a probabilistic forecast. And then basically for each prediction, we have two probability distributions, which we plug into an optimization engine. So one of the simpler approaches that we can do is basically use Monte Carlo simulations. So for each sample we draw, we combine the distributions and use the formula we discussed before to calculate the cost. And this is pretty much this in a very big nutshell. I think there are way more intricacies here than I can actually discuss now. But of course, this is not the only approach there. So, well, there's also nice research by Pierre Pinson about the alternative approaches to this, and you can also see a reference here. And yeah, with this, I think it's time to wrap up and talk about the key takeaways. So first, I hope that I showed you that probabilistic forecasting adds value by enabling risk-based energy trading. So if we account for our risk appetite and also the potential trade-off between losses and gains, we can make better decisions, which can in turn help with stabilizing the grid. Then I showed a few approaches how to actually create probabilistic forecasts, so 3 or 4 approaches in the baseline approach. And lastly, I hope that you also see that probabilistic forecasting can help accelerate the transition to renewable energy sources. So yeah, with this, I would like to conclude. Thanks a lot for your attention, and yeah, I will answer any questions you might have.
Thank you very much, Eryk. Very, very interesting story. Do you have any question? We still have a few minutes. Yeah, many questions.
Thank you for your presentation. Great presentation, though. I just wonder, have you tried other methods like based on some theoretical underlying distributions, like when you assume something before running your experiment?
No, not really. We haven't tried that. So that's also because, yeah, those distributions tend to also shift all the time. Mm-hmm. So no, we haven't.
Okay. Okay. Thank you.
Who else?
Any other questions?
Have question? Yeah. Okay.
Yes, thank you for the presentation as well. I don't know if it's really relevant, but is the problem of fat tails distribution relevant to this case? And does it appear in energy markets in this specific case?
Yeah, sure. Indeed, it does. So that's also what we try to account for when predicting all the percentiles or quantiles. We do observe fat tails in the fat tail distributions, and that's also what we try to account for in our optimization engine. So whenever we are forecasting the distribution, we do account for it there. So we also use different metrics that might be used in, for example, quantitative finance, to evaluate the distributions and then also use them for, well, better risk hedge trading. I hope that answers the question.
Okay. Any more questions? Yeah.
Hi, thank you for your presentation. I actually have a question about the weather data that you use to predict all of those things. As we know, weather forecast is not really accurate as well. It's prone to biases and so on. So do you take an account of those, or do you just trust your model to learn those inconsistencies in weather data?
Yeah, that's a very good question. So indeed, that's what we are trying to do. So as I mentioned, there are quite a lot of weather features that we can take into the model, and to also account for some biases, we tend to take well, for example, the same feature, let's say humidity from different weather models. So then also if, for example, one model has some kind of a bias or inaccuracy, we can try to compensate with the other one. We also try to create features combining different weather models. There's quite a lot of, probably like a dozen or so commercial weather models that we can use. So we try to use as many as we can and see basically if that improves our performance. But of course, weather data is highly unpredictable. Well, in the Netherlands, you can expect a sunny day. You see it outside of the window that it's sunny, you go out and it's raining. So that happens quite a lot. So indeed, it is a big challenge, but that's how we try to account for it.
Okay, yeah.
Thank you for the presentation. I wanted to ask you about this rolling window conformal prediction. Could you tell us more about how it's done? Because this data is autoregressive, and for the conformal set, how do you pick the data samples between the time steps? How do you do it? Could you tell more?
Well, that's a very good question, and to be perfectly honest, we don't really do that. There is a reason for this, because we tested this out and it didn't really work that well in practice. So what we are doing is we ended at the quantile prediction, and then we use that for the optimization. So, but yeah, so I don't really know how to answer that question, but yeah, I think you can experiment with different window sizes. So that's something that we have done at some point, well, before I joined the company. But yeah, I can't answer it any better, sorry.
I'm curious for the power usage. How do you handle singular events? For example, Taylor Swift flies in and she has a concert, and that will bust up the usage. Like, how much tinkering does that require, and to what extent can you statistically handle that based on previous such events?
That's a very good question. So, of course, in advance, it's very hard to know what will happen. So what we do is we try to afterwards remove those, either account for or remove those observations from the training data. So for example, it happened, I think in June somewhere, that there were massive floods in Germany, and it caused a spike of the energy prices to pretty much something we've never seen before. So of course that was unpredictable at that point. But then in order not to contaminate our training data, we either remove this or try to add some features that will actually explain what happened. But with those singular events, as you mentioned, most likely it's just removing, because yeah, it's very hard to predict if a concert will cause a spike or if a flood will happen. Well, if we knew that, of course that would be, well, a big money-making machine, but it's very hard to predict those things. Any other questions?
Okay, so thank you once again for your presentation.